Hello, everyone. Good afternoon. Welcome to the second session of the User Designer track for VLSIT 2022. My name is Subhash, and I'll be chairing this session. And so we have five excellent presentations lined up for you. And just a few notes here. So the presentation will play first. And if you have any questions, please type them on the chat window, and I will be taking them on to the presenters who are live with us. So without further ado, let me introduce the first paper. This is what we have as the first of UDT 2.1. It's an end-to-end FPGA prototyping for a flexible, configurable, and scalable solution for software development, integration, and system-level validation. And it's authored by Mamta Garg, Sujit KV, and Patnana Y Rao from Intel. So stay tight, and over to you for the start of the presentation. Right.
Good morning, good afternoon, everyone. Myself, Mamta Garg, along with my co-authors Sujit and Yogi from Intel Technologies, are here to present our idea on end-to-end FPGA prototyping, a flexible, configurable, and scalable solution for software development, integration, and system-level validation. It's absolutely an honor for us to be here in this prestigious event and share our idea with a wider audience. So we have kept very pretty simple agenda for today's discussion. We will start with the problem statement, and then we will go to the solution which we are proposing, along with few details of the solutions, the benefits which we see that our solution can bring, along with the results which we would like to mention as a data points which we have observed in our project. And at the end, we would like to mention some of the acknowledgements and next steps for the solution. So design complexity increasing day by day. It poses lot of challenges for software hardware co-validation, and it becomes difficult for to manage hardware and software co-validation development along with the execution. Generally, all SoCs have one critical software component called boot ROM that is burnt along with the SoC. The bugs discovered in this boot ROM are often translated to respin of the product, which bring lot of monetary loss for the company. That's why the quality of this piece is uncompromisable for the success of the product. And traditionally, we have used FPGAs for IPs and subsystem hardware and software validation, software development and validation, because these FPGA prototypings provide you a capability that you can connect a real devices to this FPGA boards. So this provides you a capability to do hardware and software development and validation. But as you know, any FPGA is not a push button process at all. Putting a design onto the FPGA, it takes lot of planning. It takes lot of effort to customize the RTL to make it FPGA friendly. Thus, it takes longer bring up times, high turnaround time, and late availability. On top of that, today's complex SoCs are not possible to fit into single board FPGA. We often take like multi FPGA boards to prototype one SoC. That's why it results into less performance and it creates a bigger risk for the project milestones. Other than that, iterating software on FPGA requires multiple rebuilds and patches. Every time there is a change in the boot ROM binary, and if you would like to run it on a FPGA, you have to do a patching, and once you do a patching, it takes time. It takes 1 to 2 hours. So every build takes 1 to 2 hours. So that's why it's costly in terms of efforts, time, and cost. Thus, it's very essential to have a robust pre-silicon platform which should be robust in nature, which should enable hardware and software co-validation, which should enable software teams to start their development early and enable OS level scenarios. Once you enable OS level scenario on a pre-silicon platform, it will enable you to find a corner case bugs. It will enable you to do hardware software co-validation, and thus it will bring efficiency and better time to market. To solve all these problems, we are proposing our solution here. We have used this solution in our product. So we are naming it as a hybrid FPGA prototype, which is a combination of hardware and software domains. In the hardware domains, we have the IPs and the subsystems, which are cleaned from a timing point of view, which have been synthesized for the FPGA. And these FPGAs, we are connected with the real peripheral devices, which we call it as a daughter boards. And this complete, we call it as a HAPS platform. This HAPS platform, we connect it with the help of hybrid infrastructure stack to a virtual platform. Virtual platform is a software modeled your SOC view. All the components of the SOC are modeled in a software world, generally like System C and a TLM, and in Intel we use a different technology for that. But the models are written in a software world, and we call that as a virtual platform. Both this virtual platform and the HAPS platforms are connected together with the help of this hybrid infrastructure stack. And this hybrid infrastructure stack has two layers, software domain and the hardware domain. So let's look into what is there in this hybrid infrastructure stack also. So as you can see, this hybrid infrastructure stack have these components. It has a transactor. Here we have used a Synopsys transactor, and we have modified it according to our needs. With the help of transactor, user can map the devices from VP domain to the FPGA domain and vice versa. We have developed a fully customized FPGA interconnect that we have developed in-house, and this interconnect has support of, it supports the multi-protocol, it's fully configurable architecture, it supports the address map configuration at runtime, it supports faster customization of the multi-FPGA model variant, and because we have developed this in-house, it supports us to do easy synthesis and timing closure. So with the help of these components in the hybrid infrastructure FPGA stack, user can map the devices with the help of a mapping file given provided to this transactor. User can map the devices from VP domain to the FPGA domain or FPGA domain to the VP domain. That's the main USP of this solution, that user need not to rebuild FPGA again and again. If some IP is not functional in the FPGA due to some RTL issues or due to some issues, so software team can use the same FPGA, but they can map that particular peripheral in the VP domain till that time the bug is fixed in the RTL, and they can continue their software development. Once the RTL issue is fixed and the IP is stable, we can again put that back onto the FPGA and provide them a new bit file. So here we would like to reiterate the benefits which we have seen of this solution, along with some of the recommendations from our side. So traditionally, hardware and software development, if it happens in a sequential order, finding a bug during power on will bring lot of challenges like respin, the time to market pressure, and the cost implications. That's why we are providing three recommendations from our side. First recommendation is that start virtual platform development along with the architecture. This will accelerate the software development. This will enable software teams to start their software development early in the design cycle. The recommendation number two is start FPGA or a HAPS development along with the hardware validation. This will accelerate software integration and validation. Software teams can use this IP FPGA or a subsystem FPGA along with the hardware validation, along with the RTL verification timelines. The third recommendation is to basically combining both of these things together, combining best of virtual platform, combining best of FPGA, and build a hybrid FPGA platform. This hybrid FPGA platform is SoC level solution That's how it will enable you to do system level use cases bring up on this hybrid FPGA. And you can map, because of the fact that you can map the devices at runtime, so it will enable you to do lot of software integration validation much early in the design cycle. That's how you will be able to get more window for the system integration. You will be able to do early system integration. You will be able to integrate all your software stacks much early and create a BKC images out of that. And that's how it will enable you to do time to market. It will enable you to do faster PRQs for your product. Just to summarize, these are the benefits of HFPGA. It will allow you to do early system software integration. It will allow you to do more cycles of hardware software co-validation, and that's how it will bring a silicon quality confidence and faster time to market. Here are our results which we have observed in our project, and we would like to share with you that we have seen a 2x gain in the build turnaround time compared to the classical FPGA builds. Because this is a HFPGA solution, we are not doing a full SoC onto the FPGA. That's how we could see a lot of build turnaround time. We could see the low overhead in the new HFPGA interconnect generation time, which enabled us to do faster debug, and 30% less iterations in the FPGA build, which resulted into saving of the compute resources. And because this is a HFPGA, this is not a full SoC FPGA, it helped us to improve the model performance from 1 megahertz to the 5 megahertz. Now, because the model performance increased, so it helped us to accelerate the boot ROM validation by 2x. We could execute the BL1, BL2 image executions. We could run the BL1, BL2 image execution in just 10 to 20 seconds. It allowed us to do more cycles for system integration validation, and we use this platform for the test content development for the post silicon readiness also. On this platform, we could run all end-to-end use cases, which eventually helped us to do a quality confidence for our silicon. As the solution is easy to scale, the solution is flexible, user can map the mappings at runtime, it's highly configurable, and it mimics the full SoC view. That's why we are calling it as a flexible, configurable, scalable, end-to-end FPGA prototyping solution. At the end, we would like to definitely pass our sincere thanks to the partners who worked with us, our EDA vendor, Synopsys, who worked with us on their HAP solution and methodology enablement, on their support to enable this hybrid infrastructure, our hardware teams who worked with us on the hardware validation before putting the design onto the FPGA, our software partners who use this solution for their software validation, which help them to achieve a better quality software. And we have listed some of the next steps also. As this solution mimics the whole SoC platform, this can be extended to be used for the SoC performance validation also. And this will be a good extension of our solution, and which can bring lot of good ROI in the PNP validation scope. Along with that, we would like to propose this solution to be used by our sales team as a pitch for our products demonstration to the customers. So with this, we would like to give our thanks to the VLSI design team also, that they given us the opportunity to share this idea. And with this, we would like to end. Thank you. We are open for the question answers. Thank you.
Thank you, Mamta, Patnana, and Sujit. That was a very good presentation. And while while people are forming their questions and if they're typing them, I have this solution is actually very close to in fact what we use HAPS also. So this is a very, very interesting one. So I have one question here. So like your virtual, I mean the hybrid model, right? Is it like a user, like somebody who's using, like let's say your software person, he can decide which one to dynamically use, your virtual one or the real RTL kind of thing? Probably that's is that level of flexibility is there in this solution?
Yes. So at the runtime, for example, if first we actually give this complete platform to software developers and validation
Mhm.
engineers. So when we give
Mhm.
them, we actually give them basically there is a file where you have to basically specify the mapping, which IP has to
Mhm.
be basically mapped, and this IP has to be mapped, and this is the address whether you want to map that address to the virtual platform or whether you want to map that address to the hardware domain. If you will not map anything to the, let's say for example, anything to the virtual platform, automatically the will go to the hardware side. But if you want to map anything to the VP side, you have to specify through that files or particular that peripheral on the virtual platform side. And this is like the user can do it. There is no need the user to come back to the model or maybe the platform builder to make that change. This is a runtime file which user can make the modification.
Okay, very good. So, so is this like a homegrown solution, or is it something that, I mean, HAPS I know is Synopsys, but it's a mixed solution, or is it a complete homegrown solution that you have?
This is actually a mixed solution. So in
Mm,
terms of methodology, we have used like HAPS methodology, as we
mm,
have told in the presentation also.
mm,
Transactor also, like some part of the transactor have been delivered to us by Synopsys, but we have to basically massage the transactor to meet our requirements. And then the basically the interconnect part which you have seen in our solution, so that is homegrown interconnect which we have developed
mm,
because of to meet our requirements, because we wanted to have a configurable thing in that interconnect. We wanted to support multiple protocols so that we can reuse that same interconnect from one project to the other project also.
okay,
So
okay, okay.
it's essentially a mixed solution. So but like most of the HAPS proprietary part is actually which Synopsys has
Mm.
helped
Uh,
us to enable.
sure, absolutely. So, yeah, I mean, so one more question on this one. So, today you see the usage. Where is the usage? I mean, most use of this, is it during your shift left of your software development, or is it more like in your debug of your RTL in the end-to-end scenarios? So where is this, or
No,
where do you see maximum usage?
yes.
Because I mean,
So
this is,
this is yeah, I got your question. So basically, the we are not giving this solution to our hardware teams to do the validation.
I see.
That's not basically the intent here.
Mm,
Intent here is for the software developers and the software integrator and validators who wants to do lot of shift left in their software cycle. Plus the other intent which we have it is to basically do a hardware software co-validation. So for
mm,
example, we want to run a full OS stack on a system, and that system is this platform actually, where we are giving them the capability that user can run the full OS stack. So once we do that, obviously we might find some corner case hardware bugs also, but that's not the intent
mm.
actually. Over the course
Okay.
of execution, we might find some corner case hardware bugs, but the main objective is for the software teams. Along with that, we give the solution to our post silicon teams also, who basically for their post silicon test content readiness, they use this platform so
Mm.
that they will be ready once the silicon will be available to them. They will be ready with their test contents actually.
Okay. So thank you. Thank you all. I think that's all the questions, and thanks a lot. Excellent presentation and very useful, and relevant to many of the folks in the audience also. Thanks once again for the excellent presentation on the paper, and
Thank you.
we'll move
Thank
on
you.
to the next session.
Thanks Subhash and others, all the VLSI team. Thank you so much. Thanks to my all co-authors also.
Thank you.
Bye.
Thanks, everyone.
Okay, so after that excellent paper on the FPGA prototyping, we're moving on to our next session. This is a UDT 2.2 paper presentation. It's on robust detection of leakage currents at cell and device levels. And the authors are Akshita Bansal, Jerome Lescott, and Atul Bhargava from ST Microelectronics. Okay, let's go ahead and look at the presentation now.
Hello to all. I am Akshita Bansal from ST Microelectronics, and today I will present to you our work on robust detection of leakage currents at cell and device level. So first, I will explain to you the problem statement. So for SOC designers and big IP designers, the main issue is to detect the leakage current with minimum manual effort. So the key here is to generate the probe file in such a manner that the runtime for simulation is less and the waveform file generated is manageable enough so that we can parse it and understand where exactly the leakage current is coming from. The second part of this problem is to identify exactly where in the hierarchy this leakage current is coming from. So for this, we need to navigate the design hierarchy and generate the report in a user-friendly manner. So this is the problem statement that we will be tackling. And the context of work, the solution that we have generated works for all EDA simulators that are present today in our company. And we support both analog on top and digital on top type of designs. So the solution that we have developed, we call it iWays. It tackles the two problem statement in the same manner, that is in two phases. In first phase, we will generate the probe file smartly. And in the second phase, from the waveform file, we will generate an interactive report, which today we are using a spreadsheet Excel kind of report, in which we will populate all the current values and we will display it in a manner which is understandable for the user. So today we work on Spice and Spectre type of netlist, and we take this file as input for iWays. iWays will parse the netlist and generate iWays.probe file, which is compatible with the netlist syntax provided as input. So it can be plugged directly into the netlist. Then user can use any of these simulators to run their simulation. It could be analog simulator or AMS simulator. And once we have the waveform file, either in FSDB or WDB format. Then we take that waveform as input in iWays and we generate our report in which we would have current values corresponding to each of the generated probes. So now I will dig a little deeper in the phase one of our flow, where we are generating the probe file from our netlist that is provided as input. So for each netlist, we first have to identify the device under test. So we provide some command line arguments using which the users can either provide us a device under test, or if they simply want to run the probe generation without giving any constraint, then iWays is smart enough to identify the device under test by identifying the device with maximum number of pins. Once this DUT is identified and we have the list of top level nets, then we traverse down the hierarchy through these top level nets up to a certain depth, which either can be specified by user or by default we keep a specific number so as to keep the profile to minimum. Please do note that this profile generation is for cell level, so we don't go down to primitives, so we don't generate any probes for primitives. The contribution of current from primitives is taken into account, but the probe from primitives itself is not generated. So as you can see in this diagram, iWays will traverse from top to bottom. So for each pin that it finds, it will generate a probe and add it to the probe file, to this iWays.probe file, which can be in turn plugged inside the netlist right before simulation, as we discussed very briefly in previous slide. So as I mentioned, for every sub-circuit pin found, we generate a probe. And in case there's a shorted resistance, then we follow that net and we generate probe for each of the net that is found in the path of that shorted resistance. There's possibility to provide multiple constraints by user. As I already mentioned, we can have a constraint on hierarchy depth that we want to pass. We can also put some constraints on the basis of net name or instance name. For example, we can black box a certain cell completely and ignore all the probes corresponding to it. Or we can treat it as a gray box. For example, if you have a shorted resistance going through that particular cell or instance, then we only follow the shorted resistance, but we don't generate any probe for any other pin of that particular instance. So we provide a lot of flexibility with this process of iWays.probes generation. And by default, if the user doesn't give any constraint, then I already mentioned we choose the DUT ourselves and we generate the probe for default depth of hierarchy. And the user can plug this iWays.probes in the simulatable netlist. Now that we have run the simulation and we have the waveform file available, we call again upon iWays. We need to invoke iWays for phase two. So here we have either the WDB file or FSDB file available based on the simulator that user chose to run the simulation. So today we are using either EasyWave or WaveView waveform viewer coming from EDA vendors to parse these waveform files. So to parse this waveform file, we need a mandatory multiple time window or a single time window input from user. This time window should be within the simulatable time. This is to provide some flexibility to user and also to reduce the data that they have to analyze when we are analyzing the current values. And of course, we can compare the multiple time windows to understand exactly under what conditions we are getting the unexpected current value. So to make the computation of average currents faster, we can divide our probes by number of jobs. So this would make the matter of parsing, like say for thousands, 25,000 probe, a matter of few minutes, like 5 to 10 minutes at max. So this is the computation power that we are talking about. And once we have the Excel file generated, then it is a very interactive report. You can hover over the Excel sheet and you can look at exactly which net is generating the current, and it provides you the hierarchical tree from the top net to the hierarchy where the current value is generated. So the designer would know exactly where in the design this leakage value is coming from, and they can go in their design and fix it, and everything would be fine. So this is very useful in front-end validation, and it is already in place and being used by our customers inside SD. And also, while generating report file, we provide certain constraints for users so that they don't have to run simulation over and over again just to view a more refined Excel sheet. So apart from providing window, they can also provide the threshold current values below which they don't want to see the current values. They might want to play with probes per job so as to further reduce the runtime. And they might want to specify certain unit for current, or they want to exclude some nets, so they don't have to run the simulation again. They can simply run the report command, and it would take them a couple of minutes to generate this Excel report. So up until now, we were talking about cell level. Now, this is something new that we have implemented for our backend designers, which is to generate a CSV file. So we already compute average currents. You're already generating an Excel sheet, and we also have a CSV file with those current values for each probes. Now with Cadence, we have an electrically aware design based routing where we can populate the average currents for each probe inside this Cadence utility. And we can see these current values when we are routing our design in layout. And we can also back annotate this on our schematic view. So once we have the CSV file available, iWays also provides you with a parser which would convert this format in EAD compatible format. So basically this flow that is provided by Cadence is known as more popularly as simulation driven routing. One limitation that was for our designers was that this only was provided for ADE and Cadence environment, whereas the designer might want to use Eldo simulation or some other simulator to run the simulation in batch mode, and they might want to play with netlist more. So to provide that flexibility to our designers, we have provided this bridge using iWays, where iWays will give you flexibility to use any simulator you want, and it will generate the CSV that is compatible with Cadence. And you can use this CSV to populate it inside EAD. And once you create the data set based on the CSV file, you would have all the current values, and you can back annotate it on schematic, and you can also view it in layout while doing your routing. So this is very helpful for backend designers, and they don't really have to depend on front-end designers to get and generate the current value because this is so straightforward. So in conclusion, in iWays, we have developed a smart solution for both front-end and back-end designers for validation and electrically aware design. The designers don't need to drastically alter their process to validate their design for any leakage current. For back-end designers, they can work directly with netlist provided by front-end designers without worrying about hassles of different simulation environments. And we have observed a great saving in manual efforts of our customer with a projected gain of 10%, which was given to us by our backend designer specifically. So as you can see in this flow chart, the front end validation, you don't really have to go outside of your flow to use iWays. It fits right into the flow, and you can use iWays to validate your current. And if you're a backend designer, you can use the current CSV file to see that the wire width that you're using are compliant with EM requirements or not. So thanks a lot for your attention. And if you have any question, please feel free to ask.
Thank you, Chita. That was a wonderful presentation. While waiting for the questions from the audience, I'll have a few of my own here. So few questions. The first one, what was your development platform? This iBase 2.
So I suppose you're asking about the scripting language that we have used.
No, I mean, what, like, is it a language or what's how did you develop this tool? In what is it, in Scale or that way?
Yes, so the API is in Shell, so Shell Python script, and usually we run it in batch mode on Unix, and the results that we generate can be plugged inside the EAD environment of Virtuoso.
Okay. So the second question I have is, like, you mentioned this splitting into multiple LSF jobs, right?
Yes.
Is this is this automatic, or I mean, how does that work? I mean, how do you partition the jobs into multiple things in?
Yes, so that is automatic. If the user doesn't provide us with any constraint, I mean, the user can specify how many probes per job we can consider. And of course, if there are less number of probes per job, then there would be more number of jobs in parallel, and it would be that much faster. And we would be only limited by license availability. But if the user doesn't provide it, then also we do it internally automatically. We, for example, if you have thousands of probes, we divide it into 1,000 probes per job, and we launch those many jobs in parallel. So we do have an automatic internal number if the user doesn't provide any constraint, but we do provide user with flexibility if they know that, okay, licenses are available and they want it quicker, then they can provide us with that constraint as well.
Okay, excellent. So, okay, I have one question from Mamta here, or actually a two-part question. So, what's the primary motivation for your solution? Is it to help front end or back end or both? And the second part of the question is, how was it done in the past, in the absence of your iBase solution?
Okay, so thank you, Mamta, for your question. So with iWays, we propose to provide solution for both front-end and back-end designer. So for front-end designer, the idea is more for front-end validation, just to ensure that when their design is complete, for example, on SOC level, their design is complete, and they run iWays, they can identify exactly where the leakage current is coming from. For back-end designer, the requirement is very different, but we are still using iWays because the solution that they needed is based on current values. So when they do the routing in backend, if they have the current values available, they can choose the width of wires to fulfill the EM requirements. So we extract these current values from the front-end netlist. Of course, we can also have some models for parasitics in the front-end design. And even though you can argue that it is not accurate because it's ideal netlist, we don't have parasitics yet, but still it gives a very good idea to backend designers that, okay, this could be the estimated current, so they can take some margin based on models or based on their own experience and understanding, and choose the width of the metals such that they can fix the EM before the design is complete, and it's too late to make any changes. So that is the idea. So the main core concept is that we are extracting current values from the circuits very quickly. It helps the front-end designer to validate their design, and it helps the back-end designer to make a more current-aware design on the basis of currents that we automatically generate for them. And they don't have to rely on front-end designer to extract these currents. So they don't have to go back again and again in iterations. It's very simple. Once they have the netlist, they can straight away run the simulation. They don't have to care about constraints because there are some default constraints already present in iWays based on our experience. So they can simply run the flow, get the current values, and get on with their day. So the second part of your question is how it was done in absence of iWays. So for front-end designers, it was an issue. We did face some major issues. So this request was raised a few years ago. For back-end designers, mostly this request was coming from IP. So their design was comparatively a little less, but as I mentioned, there was a loop they used to request the front end designers for current values, and then in EAD, I think okay, SDR is new, but EAD has been there for some time, so they plug in those values manually, because even if they get the current values from front end designers, they have to feed it inside EAD in the set format, right? So they had to extract those current values from ADE environment, and they were also limited by the environment itself, that they had to run it in Cadence environment. So there were some limitations, but they were able to get by. So we have removed those limitations, in the sense they can use any simulator they want, and everything is in batch mode, and the are already in a format that is compatible with Cadence. So that is how we reached this gain value, this projected gain value, based on some experiments that we did with our backend designers.
Thank you. Thanks a lot, Akshata. A lovely presentation and great questions and the answers from you. Good luck, and also thanks for the presentation and the detailed answers. Okay. Thank you. We will move on to the next presentation, which is UDT 2.3, and that will
Thank you so much.
Thank you, Akshita. Yes. So enabling in-memory computing with new energy-efficient assist sense amplifier for Boolean computation in SRAM array. That's a mouthful. Okay, so this authors are Kavita S. Santosh Kumar Vishwakarma and Bhupendra Singh Reniwal. They're from Indian Institute of Information Technology, Kanchipuram. Okay, so let's move on to the next presentation.
Hi all, this is Kavita. I am here to present the topic enabling in-memory computing with new energy efficient assistant amplifier for Boolean computation in SRAM array. We all are aware of what is one-Neumann architecture. Here we have separate memory and logic blocks. Whenever we need to perform computations, then we will do it in logic block by fetching the required data from the memory block. This to and fro movement of data from the memory to the logic block adds on the bottleneck of von Neumann architecture. This bottleneck increases the energy consumption and increases the computation delay. From the graph, here you can see the relative performance plot. There is a large difference in the speed of processor and memory. So because of this differences, we have some performance gap over the period of year. To eliminate the disadvantages or bottleneck of von Neumann architecture, we are moving on to the in-memory computing. In-memory computing means performing the computations inside the memory. So this has its own advantages like parallel data processing, low energy consumption, and low computational delays. Here you can see there are two types of memory, charge-based memory, resistance-based memory. In charge-based memory, you can see we have SRAMs, DRAMs, flash memories. In resistance-based memories, we have resistive RAMs, phase change memories, and ferromagnetic memories. In order to perform the required computations by enabling the in-memory computations, we configure the sense amplifiers in the SRAMs. We can use asymmetrical sense amplifiers to achieve the required operation, but it has its own disadvantages by adding more delay or latency to the circuit. This is the overall architecture of SRAM based in-memory computation. So here we have 16 cross 16 array of SRAM array, and all the SRAMs are stacked up to form this array. Here we have pre-charge circuit to pre-charge the bit lines. Then we have row decoders, column decoders to access the corresponding row or column memory cells. Then we have WBL, WBL bar, word bitline and word bitline bar to write a specific data into the desired memory cell. RBL bar, read bitline bar to read the data from a specific memory cell. The write operations is done using write drivers. The read operations is done using sense amplifiers. Here in this circuit, I have used 8 plus 2T, 8 plus T transistors. The timing diagram of the 8 plus T to read, write all the different timing diagrams are shown here. Then here we have the truth table of the desired Boolean computation. Here we have digital truth table of digital logic of AND, NAND, or NOR. So based upon the input that is being stored in the memory cells, the required Boolean logic can be computed using SRAMs. Then this is the proposed assist sense amplifier for in-memory computations. Here we are using MUX to control the desired operations that are to be performed. Here our major operations are NOR or OR, NAND or AND. So both things can be computed since we have our sense amplifiers output and output bar. So if one is giving the output of OR, the other will be the complement of it. So based upon the select line input of the MUX, the required input will be sent to the sense amplifier. Based upon the inputs, the sense amplifier output will be these operations. To perform the normal thing also, we can have this. So now let us take an example. If both the assist MUX, like assist MUX have inputs have 0, 0, select lines have 0, 0, then the input of A and B will be of A and B will be RBL 0. So here RBL will be there, here 0 will be there. That means RBL and this 0. So this transistor will be off and the required NOR or OR operations will be performed. So by adding these two assist transistors, we are able to achieve both NOR or OR operation, then AND or AND operation. Just by changing the input values, we are able to achieve both the things using only a single sense amplifier. And there is no disturbance in the normal read cycle. So we are able to achieve this using with the help of the MUX that we have added, and these operations are majorly based on RBL and RBL bar. That is how the RBL and RBL bar discharges for different input cases. In this timing diagrams, you can see like when it is 0, 0, your RBL bar is at VDD and the other one discharges. Other one in the sense complement. The vice versa happens for input case 1, 1. But in the case of input 0, 1 or 1, 0, both the things will be discharged and your sense amplifier will be tuned in such a way that you are getting the desired operation. So when your sense amplifier is enabled based upon your desired thing, we will be able to get the desired operation. If RBL input A is RBL, input B is 0, input then the first one is NOR operation, the second one is NAND operation. Here we have shown the simulation in output of Monte Carlo simulation for 1000 samples. We have even simulated for different cases and checked all the simulations output. And then we are moving on to the result section. Usually our circuit should be energy efficient. From the plots, delay, average power, power delay, product, we can see that our circuit is energy efficient also. We have compared our circuit with two other circuits. One is asymmetrical sense amplifier, the second one is common CLSA with 4+2T SRAM. Here you can see our assist thing will have very lesser delay when compared to CLSA or a symmetrical one. So the delay is also very low for different VDD. Then we are moving on to the average power section. For different VDD, you can see that our assist have power consumption is low, but it is not as low as this because of very less number of transistors that has been used in the SRAM. That is, in this case, we have used only 4+2 T SRAMs, but in our case, we are using 8+T transistors. But if you see, there is we have some difference, but it is negligible. But when we are comparing the overall PDP, here you can see that we are able to achieve a greater difference when we are comparing it with the asymmetrical thing. Next, we are moving on to the reliability analysis. Here you can see that we have simulated the Monte Carlo simulation of delays for 5,000 different samples, and in that 5,000 how we have got the results. The standard deviation is very less when we compare with the other design. Then we are moving on to the yield. Yield, if you see, yield is the number of success rate, percentage of success. Here we have simulated the yield for different process corners. Slow, slow, typical, typical, fast, fast, slow, fast, fast, slow. Then here you can see that this is the worst corner. For the worst corner also, we are able to achieve more than 97-98% success rate. But when we are comparing with the asymmetrical or the CLSA, we are not able to achieve more than 95% also. So, and on average, if you see, our assistance amplifier have good better yield when compared to the other one, and that too in your worst, if you see, we are able to achieve 98% success rate. Then this is the layout of the symmetrical sense amplifier. Here we are adding the mux which adds on the area of the overall circuit. But if we see, there is a need of two sense amplifiers when we are in a need of computing two different operations like OR and AND. If you see, for OR we need a separate sense amplifier, for AND we need a separate sense amplifier. That disadvantage is being resolved using this mux. These applications, here you can see these are some of the applications. Wherever we need to process n number of data, their in-memory computations will be very useful. Here you can see autonomous vehicles, human intelligence executed by machines, medical image processing, etc. So these are the some of the reference which I have simulated for my comparison. Thank you.
Okay, thank you, Kavita, Bhupendra, and Santosh. Excellent presentation. So, while audience are thinking about the questions, I have a few of my own. First question is, how did you arrive at the yield computation?
Am I audible?
Yes, yes.
I have simulated the test cases in Monte Carlo for different process numbers, and the number of pass rate by total number of test cases. For example, if it is 9 in 10,000, I am getting 98% pass rate. I am neglecting the negative rates and checking how many test cases are getting passed. If the output should be 1 for the desired thing, for example, in AND for 1 input we need 0 has output. So in that case, if it is like the sense amplifier is able to detect that value, then we will be able to say it as pass. If it is not able to detect in like different samples, we'll be giving like 10,000 samples. In that 10,000, if like 999 samples, we are able to get it as like expected 0, and one it is not able to, then we will say like 99.9% as success.
I see. Got it. Okay. Very good. So I had so extending that question, right? I mean, any theory from your side on why CLSA yield was so bad compared to?
Because there was a need of setting voltage. Like here we have the need, like there was two RBL and RBL bar, that is read bit line and read bit line bar. But in case of current latch sense amplifier, there we will have to set some reference voltage. Like only in that only one will be there, like BL. We will be sending BL and we will be like sending reference voltage, because we are setting some reference voltage to some fixed point. There was like much the failure rate was very high when we were using that. Since the discharge of, in some cases the discharge were very, like both the things will get discharged. So based upon the discharge rate in our assistance amplifier, we are checking both the sense amplifier is able to check both the things and we are getting the desired output. But in case of current latch, there was like, since that reference voltage was fixed, it was very difficult for the sense amplifier to come to like that desired operation was like failure rate was little higher than the assistance amplifier.
Okay, thank you. I think, thank you, Kavita. And that brings us to the end of the questions for this presentation. Thanks a lot for your presentation and great work. And we'll move on to the next presentation. Okay, thank you.
Thank you.
Okay. So the next presentation, the fourth paper for today, for the afternoon session, is UDT 2.4, multi-objective optimization of TFET with machine learning methods. This is the paper is by the authors Charumati V, Dr. Balamurugan, Dr. Suguna, Hemalata M, and Dr. Sriram Kumar D. And they are all from Tyagaraja College of Engineering. So let's just start the presentation for the UDT 2.4.
Good morning. Myself Charumati from Tyagaraja College of Engineering, Madurai. And my title is Multi-Objective Optimization of TFET with Machine Learning Methods. And in the era of transistor scaling, the better performing and lower cost transistors increases the market growth. And the market growth is in accordance with the Moore's law. But further scaling down of transistors has actually become difficult these days. And Moore's law is facing its end. To overcome this problem, more than more concept is introduced. With this concept, it is not just the digital data that is being handled, but it is the environmental data, which is non-digital, is also processed. So combining system on a chip and system in package is mandatory for providing higher value systems. Machine learning assisted optimization helps in achieving more than more concepts. And the semiconducting industries are actually need to handle a huge amount of data. And while adapting ML techniques to these semiconductor industries, certain issues regarding scaling, short channel effects, tunneling effects, device variability, and heterogeneity of data prevails. And my work lies in providing a solution to the problem of handling enormous amount of data. And these issues put forth the need to identify and understand the optimum device designs and scrutinize the trade-off between the multiple design targets. To optimize a device, the following steps has to be followed. The first step is to set design variables and to formulate constraints and objective designs. Later, which variable bounds are to be set up, and an optimizing algorithm is chosen to obtain the optimal solution. So my objective is to develop a tunnel field effect transistors with a multi-objective optimization framework, and to solve objectives which includes oxide capacitance, characteristic length, and vertical electric field, and to obtain a Pareto front with optimal solutions, and to compare the results using the MOO framework with existing methods. So the design variables or parameters used for designing of optimal T-FETs is listed in a table, listed in this table. Here, silicon body thickness, gate oxide capacitance, and channel length are provided with lower and upper bounds. As the off-state current of the device tunnel FET is negligible and low, it is used for this work, and the objective functions are used in this work are characteristic length, oxide capacitance, and vertical electric field. My first objective is characteristic length, as I'm dealing as we are dealing with short channeled devices. Minimizing characteristic length is mandatory, so this becomes my first objective. The oxide capacitance is in direct proportion with the drain current. So to obtain a highest drain current, I have to maximize oxide capacitance. So my second objective is maximizing oxide capacitance. My third objective is maximizing vertical electric field this is to reduce the hot carrier effect. And the next step is to choose a MOSFET optimization algorithm. The algorithm used for this work is NSGA2, which is non-dominated sorting algorithm. It starts by creating initial population, followed by evaluating the fitness. And the next step is to eliminate the unfit individuals and passing the fittest to the reproduction phase. In the reproduction phase, the fittest individuals are crossover, mutated, and the survivors of this phase are passed to the next generation. And from step 2 to step 4, there is a loop that exists until the convergence criteria is not satisfied. The fitness allocations are done by ranking procedures. Considering these green balls as the solutions obtained, the ranking is done with the solutions with the rank 1 or grouped and are called as Pareto front 1. In the same sense, n number of Pareto front could be formed for the provided objective. And calculating crowding distance is the most important step in this NSGA2 algorithm, as the crowding distance is used to maintain the good diversity among solutions, and maintaining good diversity is actually the second goal of optimization. And this is the overall process of my work. The framework says that the same design parameters are provided to TCAD simulator as well as to machine learning technique, and the results obtained are compared. The results shows that the machine learning technique is superior to that of TCAD simulator in a sense of time. That is, TCAD is more time consuming compared to the ML wrapped MOO framework. And the gist of my process is that the parameters and objectives are formed in batches and are passed to TCAD as well as to the ML wrapped MOO. The results provided by both are compared, and as a result, optimal devices are being designed. Loop exists from a batch, from forming batches to scrutinizing optimal device, and the control exits the loop when the convergence criteria is not met. And the figure 1 and 2 shows the average distance between individuals at each generation. The dots are well spread. This indicates that the diversity of the solutions of the populations used in NSGA2 is too good, and the NSGA2 algorithm is more efficient. And the figure 3 and 4 shows the histogram representation of parents for 2 and 3 objectives respectively. While using 2 objectives, a maximum of 9 children are formed at 70th and 80th generation, whereas with the 3 objective, a maximum of 10 offsprings are formed at the initial stage itself. These offsprings, these number of offsprings indicates the goals of optimization are well achieved with this NSGA2 algorithm. And figure 5 and 6 shows the Pareto trend for 2 and 3 objectives respectively. And at least one of the objective has to compensate for meeting the goals. Here, maximizing vertical electric field and minimizing characteristic length is the target, and the star indicates the optimal solutions for designing the TFET. And figure 7 and 8 shows the ML generated model results between predicted and true response. The points that lie closer to the lines have less errors compared to the points that are far away from the lines. So the predictor model used in this work is much efficient with less errors. Conclusion: in this work, MOO design flow wrapped by ML technique is developed for designing tunnel field effect transistors, and the ML wrapped MOO achieves gradient-free optimization for scrutinizing the most optimal designs of tunnel fits, and it is not consuming so much of time. And the genetic algorithm offers efficiency regarding the diversity of solutions, and there is not overlapping of solutions, and the diversity is also well maintained. Here the MOO process are automated by the ML technique. My future work is to design FinFETs for analyzing trade-off between objectives using this ML wrapped MOO framework, and these are the references of my work. Thank you.
Thank you, Charumati. Great presentation. So a couple of questions. I'm not too well aware of the TUI. So a few questions. What is the reason? I mean, are there any other algorithms being considered, or or is this a standard? I mean, why did you choose the NGSA? Right?
Yes, sir, there are other algorithms too, but with the NSGA2, the diversity is well maintained actually. But we are working with other algorithms too, which advance NSGA2. Okay.
So, ultimately, is this? I mean, in general, this algorithm and the way that you have gone about it doesn't have to be restricted to just a TFET, right? Anything with a multi-objective, multi-object optimization. Yeah. So, is there any other applications that you're looking at from this side with this approach?
Yes, so we could move to other devices too, like FinFET and other sorts of devices like surrounding TFET. And as a prior work, we have used just tunnel FET here, and in future we are trying to expand it, sir.
Okay. So, and I mean, do you know if I know this is from a university, but do you know if this solution or similar solutions are being used in the industry, or are you aware of a similar kind of solutions being used anywhere?
Yes, sir. Actually, we have surveyed certain papers and used those values as training sets. And we were able to achieve it with optimization algorithms too.
Yeah. Okay, my question was slightly different. Was like, is there a widespread industry usage of these techniques? I mean, is there somebody who in the product company, are they using these kind of techniques, or is this more in the academic domain as of now?
I think it's in the academic domain, and optimization, I guess industries are being using it too.
Yes, of course, optimization industry uses a lot. I was kind of zeroing in on this kind of work, but I think, yeah, I have my answer. Yep. Thank you, Charumati. Thanks for the lovely presentation, and thank you for taking the time to answer the questions. And with that, we will move on to the next presentation. And this is the last presentation for this session, and in fact, the last presentation for the user design track for this year. So this is a presentation from Varun Kumar Dwivedi from ST Microelectronics. It's about CLE layout development methodologies to enhance productivity of custom IOs and test chip design. So over to the presentation now.
Hello everyone. So I am Varun Kumar Dwivedi from ST Microelectronics, working as a staff engineer in Analog and IO Group. So title of my today's presentation is CLE layout development methodology to enhance the productivity of custom IOs and test chip design. So as we all know that industry trends shows the exponential growth in the complexity of chip design. So the traditional flow are not the efficient one in order to meet the cycle time. So, and we also consistently working on improving our internal layout methodology in order to meet the industrial trend. So, like some of the point I have shown in the slide, like multiple designer cannot work together and edit on single cell layout cell view, and also it's very time consuming for top level layout designer to assign different tasks and integration and repeat the same task at the various stages of layout development. So to start with, this is the comparison between the traditional flow versus CLE flow. So traditionally, for a single layout design, if he starts working on a one project, he do everything on his single cell view, and then he once he's done with all the tasks, he submit to the project. So in this particular flow, we cannot assign multiple user on a single cell view in order to reduce the total cycle time. So on the other hand, if you see the right hand side, this is the CLE design methodology in which we have suppose two designer working on a single project. So what the top level designer can do the partition in two part, and say it is assigned the left part to the layout designer A, and then the right part is the layout designer B. And once the other designer is able to complete his task, then he does the submission, and then later the top level designer review and merge. So in this paper, I have discussed the three layout methodology using this CLE integrated virtuoso utility in order to get the productivity gain. So this is the methodology one, which is the area-based partition. In this particular flow, if you can see on the left side, this is the traditional way of doing, and the right side the CLE way of doing. So in the left side, if you see, we have one single cell view, and the top level designer is manually do the partition using some text layer or something, and then he allocate the task to the other designer, and then once the both designer completed their task on their local disk, then the later they submit, and then the top level designer do the integration part. And also we have existing in-house script. Using that script, we are able to execute this integration part efficiently. But still, the number of steps are more. So if you can see on the other and the right hand side, we have one CLE flow. So on the same cell view, we have allocated the two designer and each designer are working on the same cell view. And once the other designer completed his task, then he can submit submit his task to the top level designer. As you can see, this is shown in this particular window, and then the top level designer will do the review and merge. Okay, so in this way we are able to remove one integration step from our this development and integration flow. So ultimately, we are able to gain the time, and also we are ensuring the quality and connectivity is also maintained. So and the other methodology is this the area based partition, but we have utilized this methodology in the validation part. Like in this particular project we had to fix the massive number of DRC, so a single designer were not able was not sufficient one to handle this kind of task, and the timeline was very tight. So we have divided this task into four. So the four designers were working parallel on the same cell view, and once every designer has completed his task, then he can submit his task to the top level designer, and we are able to divide the massive number of DRC into the four part, and we are able to meet the deadline very easily, and also with maintaining the quality of the project. And also because we have multiple integrated feature with this CLE utility, so we can the chances of error are very low, because whenever you start and doing some edit things on the other layout part, so it will flag the warning. So in this way there is no risk of error in this flow, and also it's very efficient one. So and the third layout methodology is basically the layer based partition. Look, we also, although it's not the frequently we get this kind of things, but sometime when we have this kind of requirements, very tough to meet the deadlines, and also the the risk of this tape out week. So this particular statement, if you see that customer has requested for metal fix, but it was for significant part of the design, and the masks were already done up to the contact. So we cannot afford to lose any mistake done during the metal fix. So because of this layer based partition, we there is no chance of touching the base layers or the any layers which you define during the partition. So you cannot touch other layers except your the except the layers which are allowed to fix or change during the metal fix. So in this way, you can see on this DRC window, only on the GDS XOR result shows that we have only done the changes in metals, and we have not touched any other layers. Okay, this is in the first go only, because traditionally if we have such requirement, we do this kind of fix, but there are chances of error, and we have to move back and forth between these things. So chances of error are high. So ultimately we might miss and we may not be able to meet this critical requirement. So this is the results of this flow. So in the using the methodology one, you can see that for the two designer, we are able to reduce one critical integration step using the CLE flow. So in a way, this is also one step which is increasing our project cycle time. So you can utilize this flow and you can eliminate this integration part. And using methodology two, you can see that if we when we didn't have this kind of approach, so we had to do the fixing part in different cell view, and later we would have done the merging part, and then it was basically kind of not efficient flow. So using this CLE, we were able to achieve this task in 3 days. So it's a very, very big advantage of CLE utility. And the last methodology, using this last methodology, you don't have to repeat the task of GDS XOR validation. So ultimately, you can see the CLE is very, very, very helpful in different stages of development of the layout, and you can use this utility at any part of your development. This is the beauty of this CLE layout development methodology. So that's all from my side. Thank you, and I am open for questions.
Thank you, Varun. Thanks for the excellent presentation. Well, I'm waiting for some of the other questions. So I have a question for you in the sense, like, is this something that is part of Virtuoso, or is it like a mixed solution, or what's this? Can you throw some light there?
No, it's a part of yes, it's in part of Virtuoso only. It's integrated utility.
Okay.
It's actually comes with the Excel license. Yes.
Okay, so this is a part of Virtuoso, but is it something that has been a recent addition to the flow, or?
Yes, it is in the advanced version. Yes, it's a recent addition during maybe 1 or 2 months back. Yeah.
Okay. So I've very interesting to see that. I mean, I think a lot of good stuff there. So again, can you throw some light on how the partition is done? Like, how does it partition? Is it completely layer based all the time, or is it something else?
No. It's basically user-based partition. Let's say I have one. The top level designer is handling one layout view. Okay, they have one cell view. So suppose he wants in single project the 2 designers are working. So the top level designer will allocate and divide the layout in 2 parts, depending on their the work assigned, or they divide their then
I see. So
they
it's
assign.
I see. Okay, so it's a top level designer who does the partitioning, as in like maybe like a window. It can it be window based, or it has to be like a a slice kind of thing?
Yes, and there are multiple options inside that. So one is the major one is that this cell based partition. I mean, you do the user based partition. You just divide the complete cell view in depend on your requirement, maybe 3, 4, or and any number of users you can. So each user will be effectively working on the same cell view. So it's like synchronicity server. If you know that this kind of feature also enable that thing. So
I see. Okay. Very good.
It allows the multiple users. Okay. So.
Okay. So it's also about the last part of when you're describing the advantage in the during this metal fixing, right? So where is the risk reduction coming from?
Because once we do the partition.
I can hear you. Okay, sounds.
Oh, some connection issue. So, am I audible now?
Yeah. Yes. What you are.
So yeah. So during this other partition, like I have explained, 3 kind of different partitions. So in this layer-based partition, so once I do the layer-based partition, so it won't allow other layer to touch. So it will once even you are going to let's say I have assigned from M1 to M5. So I want only fix M1 to M5. Okay. So suppose by mistake I change the PC layer or some contact layer, so it will flag the warning, and it will actually give the
or dynamically flag the warning.
Yes, yeah. So in this way you can change. So I have personally used this, and it was very good in that
scenario.
Okay.
Good. Thank you, Warren. I don't think there are any more questions, and thanks a lot for the great presentation. And thank you for taking the questions. Thank you.